Hi folks, today I want to show how a certain volume of hydrochloric acid of a known concentration can be accurately neutralized by a solution of sodium hydroxide of known concentration, and to show how the results obtained can be used to calculate the concentration of the hydrochloric acid. The technique that is used is called titration. It involves placing a certain fixed volume of the acid into an Erlenmeyer flask. And in this case, I have used a 10 milliliter pipette to pour that quantity of acid into this Erlenmeyer flask. Then what we'll do is we'll use a base to gradually neutralize the acid inside there. But we first of all need to put a few drops of phenolphthalein inside to indicate the end point of the titration, or when all the acid has just been neutralized by the base. Normally, they will use a burette to pour the base gradually into that, but we do not have that. I have with me here a 10 milliliter pipette that I've used to measure out exactly 10 milliliter of the sodium hydroxide. So hopefully I will use this to neutralize the acid inside there, okay? So I'm going to gradually pour this sodium hydroxide into the Erlenmeyer flask here until all the acid has been neutralized by the base. Right now you can see that the red color of the phenolphthalein is tending to persist, and that is indicating to us that the end point is near. So we take our time and gradually add more and more of the base until it just goes pink. Looks like it's coming there now. Yeah. So we see that a end point has been reached. One drop more. See that? So that's the end point of the titration. And we'll now read off the volume of the base that has been added. The volume of the base, it shows 5.1 milliliters. 5.1 milliliters of the base have been used. So that was a simulation of a titration. The whole objective of that titration was to find what accurate volume of sodium hydroxide was required to react with 10 milliliters of the hydrochloric acid of unknown concentration. I use this pipette here to pipette 10 milliliters of the hydrochloric acid into this Erlenmeyer flask. And this pipette is very accurate. So I know for sure that inside here I had 10 milliliters of hydrochloric acid. But we are not certain about our titration technique. That is why this experiment is repeated a number of times. So this amount of hydrochloric acid that is pipetted out into this Erlenmeyer flask is called an aliquot. So you saw I used one aliquot to do the titration, but because people are not certain about the accuracy with which they're titrating, they'll repeat this titration a number of times. And I did it a number of times before that. See, I did it 3 times. So the whole objective is to find an average volume for all the titrations that you've done before, so that we obtain a reasonable accurate volume of the sodium hydroxide that is required to react with 10 milliliters of the acid. Okay, so I'm now going to show you the results of the previous titrations that I've done and how we can use those results to find the concentration of this hydrochloric acid here. Okay, so this table here shows the volumes of sodium hydroxide that were used in the 4 trials or the 4 titrations. In the first trial, 5.2 milliliters was used, second 5.1, third 5.1, fourth 5.1. So we can disregard this one here because it is out. So what we do now is we try to find the average volume of the sodium hydroxide that was used in all 3 trials. And that worked out to be 5.1 milliliter. The objective of finding the average volume of the sodium hydroxide is to enable us to find the number of moles of sodium hydroxide that were used to titrate against this 10 milliliters of acid. How does that enable us to find number of moles of sodium hydroxide? We knew the original concentration of the sodium hydroxide is 0.10 mole per liter. Now that we have found this volume, we can find its number of moles using this formula here. Number of moles equal to C times V. Multiplying the concentration by its volume, we ended up with 0.0051 mole of sodium hydroxide. Now, we now refer to the balance equation between sodium hydroxide and hydrochloric acid. Because this equation here will give us the mole ratio that these two things are reacting by. So here you can see 1 mole of sodium hydroxide is reacting with 1 mole of hydrochloric acid. Knowing the number of moles of sodium hydroxide based on this mole ratio here will enable us to find number of moles of HCl. So we use this relationship here now, where we say given over required has a mole ratio of 1 to 1. Is 1 mole of sodium hydroxide react with 1 mole of HCl. Using this relationship here, we put the number of moles of sodium hydroxide as given. Let X be the number of moles of HCl. It does work out to be that the number of moles of HCl is equal to 0.0051 mole. Now that we know the number of moles of HCl, and we knew its volume was 10 milliliters, that worked out to be 0.101 liter. We can now use this formula here to find this concentration, where we say concentration is equal to number of moles over volume. We know its number of moles is equal to that. We know its volume was that. Okay? This volume, okay? And therefore now, the concentration is equal to 0.051 mole per liter of HCl. Depending on what type of analytical work you want to do, titration can be used in different ways. For example, you can, if you wanted to know an acid reacts with a carbonate, you can have the acid being titrated against the carbonate, and you might have other things, depending on what type of work you're doing, redox type of titration and stuff like that. So I hope that this little activity here and what we've done here today was able to make you understand what a titration really is all about and how we can use the titration to analyze different types of solutions. Thank you for listening.